back. Welcome back from the weekend. In today's module, we will talk a little bit about applications of some of the stuff that you've been learning this semester. And we'll also talk about confidence intervals. And I don't expect to finish all of this in this sitting. I might shorten it a little bit, but certainly we will go over the balance of it on Thursday. So the reading for this material, Method of Moments, Max Likelihood, is all from Chapter 9, specifically Section 9.1 in the main text. And confidence intervals can be found in Section 9.2 in the main text. So a lot of times when students go through this class and the class last semester, which is a prerequisite for this, namely stochastic computing, and then take data analytics, they're often asking me the same question, how do you use this? And so I had put together a set of slides that talks about all sorts of applications that are variations of, as well as exactly the types of things we've learned, just to show you some of the ways in which this material is used. And so this idea of standard error is related to something called hypothesis testing. And in hypothesis testing, we're basically asking the question of how typical a particular outcome, sample, or result is. And so imagine then if we had some quantity, and let's say that measured quantity might be the number of customers that walk into a store. You might want to know, gosh, is this typical for the number of customers for a given store, or is it an outlier? Is it atypical? And so how you measure this idea of typical is by looking at the likelihood that this particular example or sample that you're seeing comes from the distribution associated with the system that you have instrumented. So here we have a distribution, and this distribution is a normal distribution, which doesn't really matter to our conversation. And if we center this distribution about origin, there's the center, we can look at all the different values that you can observe for samples. Now, if you compute the mean, well, the center distribution has 0 as its mean. And then if we take the variance, the square root of variance is standard deviation, sigma. And if you go a certain distance above and below the mean, a certain distance sigma above and below the mean, a certain percentage of that distribution is under the curve within those boundaries. So let's say here's my center distribution, and there's the mean, mu, of that distribution. If I go plus or minus, so here's minus, here's plus, one standard deviation above and below the mean, if I take the area under the curve for that distribution, that represents a total of 68.2% of the total probability mass. So that would be 68.2% of the total probability mass. And so for various increments above and below the mean of a distribution, if I were to take the interval along the number line, well, all of the samples, there's a 68.2% chance, we'll say it that way at this moment, there's a 68.2% chance that any value that you choose is going to be within the boundaries plus and minus one standard deviation away from the mean. It gets even better. Well, if you are plus or minus roughly 2, which is really 1.96, standard deviations above and below the mean, that covers 95% of the total probability mass. And that 95% has special meaning in the statistics community. When something happens with 95% probability assuredness, that's considered to be assured, right? It's a sure thing. No, absolutely, that's not the same as saying 100%, but 95% is the litmus test to say it might as well be guaranteed. And so in that case, this 95% is a so-called confidence interval. It tells you that with a probability of 95%, your values are going to fall within this region that's plus or minus 1.96 or roughly 2 standard deviations above and below the center point, the mean. Okay. So this idea of hypothesis testing you can use to test all sorts of things. So that's how spam filters work. You have a distribution representing the occurrence of words corresponding to legitimate emails. And then when a new email comes in, you see what is the probability or where on that distribution does this particular new email fall. And if it's out of this 95% confidence interval, then you say, aha, this is not typical of the distribution of legitimate emails, and therefore I'm going to tag this as spam. So this is immensely useful, this standard error, for something called hypothesis testing. Suppose you're measuring heart signals. You want to know if a particular heart rate at some moment in time is typical of the patient's usual distribution of heart rates, right? You can filter out or reject so-called outliers. Okay, so another application with hypothesis testing, and this was actually a senior project, capstone project with a student I had a couple years ago, not that long ago, and it was called Physical Therapist in a Box. And the idea of that was, what if you could take your physical therapist home with you? So let's say you are recovering from maybe hip surgery or some other ailment that required you to learn how to walk correctly again. And so the idea is, well, wouldn't it be nice if you had a physical therapist with you to watch you and say, hey, wait a minute, you're leaning a little bit too much to the left, or you're leaning a little bit too much to the right, or your gait is off. Well, we use motion capture technology and outlier detection to effectively do this so-called physical therapist in a box. So we have this on-call, on-location therapist, and that was the model, perform this outlier detection using hypothesis testing with confidence intervals, and then alert that therapist that something has gone awry should an outlier be detected using confidence intervals, and now that person can contact you and ask you what's going on. And so the idea then, with this physical therapist in a box continuously watching you, you can have quicker diagnosis of injuries, and you can also get more consistent supervised exercises. So maybe you have a video and someone is looking to make sure that your range of motion is appropriate for the particular rehabilitation exercises in which you should be engaging in. And so this gives you faster recovery time. It also saves travel time and money spent because, we all know that copays are nothing to sneeze at. All right. Anyways, so this was Physical Therapist in a Box. And how did we do this? We had some motion capture software from one of the largest companies in the space. And the apparatus looks like this. As you can see, this particular subject, it has neoprene straps, kind of like scuba gear. And you see these orange boxes. Those are inertial measurement units, or IMU. They measure the movement of these boxes. And so it includes a so-called skeletal model. You have to measure the length of the joint, so the length of the this joint, the length of the shin, the thigh bone, the forearm, the elbow, and so forth, as well as the distance across the chest and so forth. And then you input those parameters into a model, and it has the appropriate measurements for the skeleton, and it tells you where exactly to mount each one of these IMUs, and it'll calculate with a skeletal model how you're moving. And so we took motion capture software to get these tracks for velocity and angular motion, angular velocity and linear velocity for each of the joints for the skeletal model from real capture data. Input that into software, and we had a set of experiments where we put a bunch of wooden shapes, if you will, strapped to the bottom of someone's shoe to make their gait a little bit off so that the left leg and right leg aren't the same length as the person is walking. And so we created a statistical model of what a healthy human being walking is, and then we quantified this idea of normal gait essentially by doing outlier detection using confidence intervals. And so it had a clear output, and the original design called for a smiley face to mean that everything is going well, a regular face with no expression to mean that everything is just normal, and then a face that was kind of like a sad face, unhappy face, to mean that something is wrong. And so part of this was the human interface design so that someone doesn't know precisely what the particular measurements are and how far off they are. That's up to the physical therapist, but you as a user can see normal, good, or bad. And an alert would be sent out if you are changed from good to bad or normal to bad. So this was physical therapist in a box, and this motion capture hardware we have in my research lab. So we only instrumented the lower trunk, and so the measurements were at the center of the hips, the middle of the thigh, the shin, and the instep, and those were the motions that we measured. And we used a normal distribution and outlier detection based on a normal distribution assumption, and we input this data into MATLAB and then played it with some other recorded data given various disturbances, if you will, blocks attached to the feet to see when we can detect these outliers, how much you have to disturb someone's gait before it's detected by outlier detection. Okay, and so this is an example of what the interface looks like. And here we have some sensor tracks here, and some of them are angular velocity, some are linear velocity for the various links, the shins, the insteps, the hip, and the thigh, middle of the thigh. And so with these tracks, they're temporal, and there are two different approaches we used for inducing a distribution, if you will. We have a sliding window, and that sliding window in one experiment was partitioned. So we have some window of n many observations, and they do not overlap. That gives us fast response, but it's not granular enough in detecting down to the 10 millisecond, 100 millisecond changes. And then this version, another version we had, was a sliding window where they overlap. And so essentially we took the measurements for each window's worth, calculated a distribution, and then did a rolling outlier detection. Okay. So there's an interesting application that uses standard error and outlier detection in a real application. Another application, managing indoor-outdoor transitions in autonomous robot wheelchairs. Now imagine if you're going from indoor to outdoor. Now a robot wheelchair or autonomous wheelchair makes use of various sets of sensors when you're navigating in an indoor environment versus when you're in an outdoor environment. In an indoor environment, if you think about it, you don't have GPS, but human-engineered structures tend to have a lot of straight edges. So for example, this doorway, let me change the pen to a different color, maybe a brighter color. I'll use blue. This doorway here has that straight edge. It has this straight edge. It has that straight edge, the straight edge for this crease or seam in the door, straight edge for that part of the doorway. Now, human-engineered structures, and there's that straight edge, tend to have a lot of straight edges, and there's no GPS. So what you can do is using some of the convolution maps, like what we've talked about, the CANI or the Sobel edge detector, you can extract the edges as features and use conjunctions or collection of edges together to describe what those door things are within an environment, those landmarks. So when you go to outdoor navigation, if you see out here, we have a tree. Now, in nature, we tend to have curved surfaces. So we see the curved surface here, and certainly the tree trunk itself is curved, right? And if you look at the shape of the tree, those leaves, they tend to be curved, and the outline of the foliage, that tends to be curved. And so you have curved surfaces. You also have the benefit of GPS, and so you can build very rich structures using different sets of features and different sensors. And so the goal is then, how do you manage this construction of features you use to interpret the world around you in a robot wheelchair when you're going from an indoor environment to an outdoor environment and vice versa? Now, certainly some of these changes can be abrupt. If you look at this first doorway here, right, you're in an indoor environment and then very quickly it changes to an outdoor environment. If you're in this atrium here, this main hall in a train station, you come inside, and let's say you want to go through a doorway, and the doorway's out this way, right, and out the main hall. Well, you have all of these features here along the walls, along the roof, but it takes a really long time before you get to the indoor environment, to the outdoor environment. And then you have something like this walkway. It's outside. It's kind of indoor environment, but it's really kind of outdoor, this weird hybrid here. And so you have these regular structures. You have straight edge here, 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 here. and it kind of looks like it's outdoor, but you're not really outdoor until you're at the edge here. And then if we look at this cathedral, while it's very tall, it looks very airy, kind of like you're outdoor, but then you have this entranceway. So this takes a really long time to transition from indoor to outdoor. This, you're kind of in a hybrid. Here, it takes a longer time. Here, it's very abrupt to go from indoor environment to outdoor environment and vice versa. And so how do you transition between the quote-unquote right features and the right ways of describing things and the right algorithms to use when you're trying to describe or categorize the world around you, i.e. around the wheelchair, when you're transitioning between these two operating regimes, these two environments? And so you can't go out and buy an autonomous wheelchair. So in my lab, my research lab, we built one. And we started out with an electric power chair, the Elite Jazzy HD, and we started out outfitting it with sensors. Now, of course, in the beginning, we worked with cardboard in this figure here, and you see the cardboard, to design what we wanted the frame to look like, because it's easy to work with, it's cheap and abundant, what we wanted the frame to look like for the sensor apparatus. So then we took that and we made some precision drawings for the rigging, and we went out and bought the stock aluminum and had the machine shop here on campus manufacture it for us. So then we got a bunch of sensors. We have a camera. There's the camera, right? That's the camera. It's a pan, tilt, zoom camera, so it can look in on objects and take pictures and use that for identifying objects in the environment. We also have some lighting, so if you're in an indoor environment, you can illuminate things for better sight. This is a GPS module. We also have a 3D camera. This is a 3D camera, and this 3D camera has a 78 by 120 array of lasers. All right, then they emit 10 dots or 10 clicks per second, and they measure the distance for the ground plane. So this is mounted beneath the armrest, sloping downwards, and as it emits these laser pulses 10 times a second, it measures the time of flight and uses that to make distance measurements, and you effectively get measurements of the terrain. And the idea there is to measure the smoothness of the terrain, because when you're navigating, you want to pursue a navigation direction that is relatively smooth. So I had a student working on a two-dimensional derivative, partial derivatives, Deshaun Crawford, and he was working on it for funded research in my lab as a student undergraduate researcher. This is another view of the wheelchair with the apparatus, or some of the apparatus mounted. There's the camera. Here's the lighting. And here is the GPS. And of course, the 3D camera, this is an example. There's a metallic mount, and the 3D camera mounts to that beneath, facing downward, okay, emitting its laser pulses. So this is the wheelchair, and here's an example. This is actually in one of the halls, Grocery Hall, and this is in the hallway. We're testing some things out. And this is the power distribution board. It sits on the back of the wheelchair. We actually designed a little shelf system that's in the back like that. It's rounded so that you don't have sharp edges. And that power distribution board sits here along with an electric bicycle battery behind it to power all the sensory apparatus. And this is the power distribution board. And the key thing to pay attention here is that this is completely undergrad driven. All of this work was done by a number of undergrads over a period of time, over a couple years. Okay, now it's about 60–65% there to be completely under computer control, but it's, they've done a great job, and the work continues. Okay, so this particular example is something called Monte Carlo localization, and this Monte Carlo localization is an approach that uses probability. Let's see if I can get my mouse to, let me see, whoops, nope, scarred, let me try this again. Now, this next slide is a demonstration of something called Monte Carlo localization. And in this Monte Carlo localization, you have a number. Oh, let's see if I can get this back. Now, in this Monte Carlo localization, you have the robot is in an area, and it doesn't know where it is. And so it's proposing, basically guessing, a number of locations where it could be, as well as its orientation inside of that space. And so this robot, let me switch to magenta. This robot has its footprint, and there's its footprint, circular. And this is the front of the robot. Now it emits laser scan, LiDAR, and each one of these goes off into the environment, bounces back, and measures the distance from the robot in that direction from various points in the environment. And so what it does is it has a distribution probability over all of these so-called laser returns, and it evaluates that probability for the distribution of laser returns on the real robot against each one of the proposed robots. So here we have a proposed location of the robot. So that's a proposed location of the robot. That circle is the footprint of the robot, and this edge here, that is the front of the robot. And now it's imagining or calculating, if you will, what the laser returns would be given that position and that orientation of the robot. So that's what each one of these is doing. So this one is doing it, this one is doing it, that one is doing it, they're all doing it. And now, given the distribution of laser returns on each one of these proposed robot positions, it compares, it looks at the likelihood for this distribution relative to these laser returns, and whichever one maximizes that likelihood is going to be the robot that survives to the next round. And so it does this again and again and again and again. Each time, those robots that more closely match the laser returns of the real robot, those will have an increased weight called an importance weight. And then eventually those that are bad guesses as to where the robot is and the orientation of the robot, those will get smaller weights and eventually drop out. And so with enough rounds and enough measurements, well, it converges onto the correct location. Now, of course, each robot is going to simulate, given its position and orientation, what the position will be if you take a step. So the real robot, let's say it takes a step in this direction, a certain amount. And that direction for that step represents a certain change in X and a certain change in Y. Now, if each one of these simulated robots makes a similar step, well, it's going to be in a new position. And then that comparison of the distribution over the laser returns with the distribution over the simulated laser returns in a new position happens again. And some are going to get weighted higher, they'll persist, and some of these proposed robots are going to get weighted lower and eventually drop out. And so over time, what happens is that you converge on one of them being the best match, and that is the localization or the identification of position in the world of the robot. So let's take a look at this. So you'll see here each one of those so-called particles is moving around. So you'll see they move around, and the robot doesn't really know where it is yet, but then eventually it will converge onto the actual location. You'll see it. Now it's located successfully. Okay. So this is Monte Carlo localization, and you can see this with arbitrary maps in a hallway. You see there's the robot in the video inset, and there's the robot in the hallway. And as it moves around, those particles move around using the same step that the robot actually makes. And it's comparing this distribution on its laser returns with the distribution of laser returns of each one of those simulated robots. So then eventually it localizes, and then you'll see uncertainty happens. It'll have a number of particles, and then it regains its track of where it is in the environment. And the more distinguishing features you have in an environment, the better and better it gets with maintaining its track. And now it's relocalized again. Okay, so that's Monte Carlo localization, and you can think of it kind of as a form of max likelihood, where your likelihood is over the laser returns, comparing that of the robot with those of the simulated robot guesses. Okay, so this is another example. It's called Copilot, and in fact, the autonomous wheelchair in my lab is inspired by this work. And this uses 3D cameras, and these 3D cameras are returning back in this inset a rendering or drawing of what the distances look like in front of the 3D camera. And so you can see here, as the subject drives past this garbage can here, you can see that obstacle emerge, and you can actually use convolution masks on 3D LiDAR data, laser returns, to pick out edges and shapes the same way we did with images. Now, of course, with images, we said an image is a relief map, but for a laser or 3D camera, LiDAR return, it's literally a relief map. And so the same edge detectors, those convolution masks, also work in extracting features that describe the environment from the perspective of a 3D camera. And so let me just play this video a little bit more, and the URL is down there. And you can actually see now, you can say, okay, well, if I'm close to some obstacle, you want to veer around it, maintaining a safe distance. Okay, so that's just a small smattering. And a lot of people say, oh, wow, that's pretty interesting. So there's lots and lots of applications for the things we're studying. All right, so let's take a look at standard error. So we've mentioned before that a statistic is nothing more than a function that's computed over data. And we say that we compute an estimator, and that estimator you can use to stand in place of that unknown ground truth parameter. And we talked about the Poisson distribution is governed by parameter lambda, the rate parameter, and then we did method of moments estimation, and found that the estimator lambda hat is nothing more than x bar. Now, this function x bar, it is a function computed from the data. It's 1 upon n times the sum of each one of our samples, xi. This is absolutely a function from your data. So you can compute the sample distribution from your estimator. And what the sample distribution is you compute this estimator again and again and again from samples. Now, you can compute the distribution of that estimator or the sample distribution for any statistic from a sample. And remember that when you take a sample, these samples can be different from one another, right? So you take that camera that's instrumenting customers coming to the store, you take a sample, maybe you take 100 samples, you get one set of values. You take another 100 samples, you get another set of values. So absolutely, these samples from one sampling to the next can be different from one another. Because these samples can be different from one another, any statistic that you compute over the samples can have a different value from one sampling to the next. And so if you were to plot the distribution over the different values that your statistic, your lambda hat, can take on, that's called the sampling distribution. So here's an example of what it might look like, and because this x bar involves a sum, the central limit theorem tells us that it's going to have a normal distribution in its shape, the classic bell curve shape. Now, this is a sample distribution, and as a distribution, it certainly has a mean, a center, and it has a variance, and it also has a square root of that variance, which is the standard deviation. So the standard error is nothing more than the standard deviation of a particular statistics sampling distribution. Now, the reason why you call it standard error, it's a nod to your audience to let them know that this particular standard deviation is not the standard deviation of a sample, it's the standard deviation of some statistic that you computed over a sample. So that's why you call it something different, because you want to make that distinction that this particular thing is the distribution, the standard deviation of a distribution of statistics, not of individual samples. And so what does this say? The standard error measures how dispersed the statistics distribution of outcomes is if you repeatedly sample and recompute it. Okay, so how do you do this? Well, you can evaluate or calculate the standard error directly, right? You can do this mathematically. You can take the variance equation, and the variance equation talks about moments, right? First moment and the second moment. So if we said that we have the standard error S of some estimator theta hat is nothing more than the square root of the variance of that estimator theta hat. So we can take this, and we know for the Poisson that the mean, mu, is lambda. The variance, sigma squared, is also lambda, our rate. We can compute the estimates using method of moments estimator or max likelihood. So lambda hat MME and lambda hat MLE, if you were to do them out, they're both X bar, our sample mean. And that's going to be our estimator that's going to stand in place for lambda. So that means we can use this X bar in place of the mean mu or in place of the variance sigma squared. Okay, so we know that the standard error is nothing more than the square root of the variance for the estimator, and we have the mean and the variance for the Poisson. We also know what the max likelihood and method of moments estimator is for the Poisson, but they're both X bar. So now, and this is in the book, we take the variance of X bar, okay? And our goal is to compute standard error, so we'll eventually take the square root of it. So the variance of X bar, well, it's just the variance. We expand out what X bar is. And the variance of a scalar is the square. It comes out as a square. So we have 1 over n squared. We'll pull that out. And then we have the variance of the sum for this numerator is the same as the sum of the variances of the individuals. So we have 1 over n squared variance of the sum, the numerator part. And we end up adding it to itself n many times, taking the variance of the individual ones. So we're adding sigma squared to itself n many times. So we end up with 1 upon n squared times n sigma squared. So that's just a little bit of algebra. So now we take that expression and we cancel 1 copy of the n in the numerator with 1 copy of the n in the denominator. This gives us sigma squared over n. Okay, so we have this expression for the variance of our estimator, our statistic. It's sigma squared over n. Great. So now, to take the standard error, we're just going to take the square root of the variance for this estimator. If we take the square root of the variance of the estimator, that's just the square root of sigma squared upon n. So now we'll make that replacement. We know that sigma squared for the Poisson is nothing more than just lambda. Okay, so now we have radical lambda upon n. All right, so we can now substitute for this lambda what this estimator is, lambda hat, which is just X bar. So we substitute lambda hat for lambda. Okay, we still have this standard error. And now we just make this replacement knowing that lambda hat is nothing more than X bar. So given that expression, we then expand out what X bar is. X bar is 1 over n times the sum of all of the samples added together. So we have a 1 over n, and we have over n, so that's over n squared under that radical, the sum of all the xi's. All right, that's a little bit complicated. We can simplify the denominator, n squared. Radical of n squared is just n. So we have radical of the sum of all of the samples over n. Great. So this is our expression for standard error, and that's a little bit complicated. Let's try a different method. The standard error of x bar is nothing more than the square root of the variance of x bar. Okay, well, we know that the variance is nothing more than, if we were to do it directly, it's just square root of the variance. Well, we have that from before. Square root of sigma squared upon n is just sigma over radical n. Okay, if we did it that way, we can now substitute this sigma with square root of s squared, because s squared is the sample variance. Okay, that's a valid substitution. So if we have that square root of s squared over radical n, we can substitute for s squared by its definition, right? S squared, well, that's just 1 over n times the sum of each of the x's minus its center. So we make that expansion, and we have 1 over n underneath that radical. So we combine that 1 over n minus 1 for the unbiased version, s squared, with that radical n in the denominator. That gives us our original expression up top. There's the sum of each of the samples minus x bar, that's the center, quantity squared. And then we have radical n times n minus 1 in the denominator. So that's just a little bit of algebra. If we look at this expression, just to kind of show you where this came from, if we look at this s squared is nothing more than 1 over n minus 1 times the sum I goes from 1 to n of x I minus x bar quantity squared. Now this numerator here, that's the same as saying radical, the sum I goes from 1 to n of xi minus x bar quantity squared over radical n minus 1. So when we take this numerator, convert it to this form, and then express it over this denominator, we combine those two denominators in one term. Okay, so given that expression, that's what we have. And we can look at this and say, gosh, well, that's somewhat complicated. So we have a choice. Either we can use this version of standard error, or we can use this other version of standard error. And that's a bit of a mess either way. This can get very complicated very quickly if you're trying to compute the standard error, which is the standard deviation of an estimator. Instead of using this mathematical approach, you can absolutely use so-called bootstrap methods, i.e. do this from the data. So that's what we're going to talk about with confidence intervals. Why don't we stop there? We're going to cut this short, and we will pick up next time on Thursday.